Okay, so welcome back. We have just finished looking at the A star algorithm, and let us look at a detailed example to see how the algorithm behaves, and in particular we will compare its behavior to best first search, because that is another heuristic algorithm, and I will leave it as a small exercise for you to compare its behavior to branch and bound or Dijkstra's algorithm and see in terms of both performance as to how quickly you find the goal node and quality as to what is the nature of the path you found, how this algorithm A star differs from branch and bound as well as from best first search. Best first search we will do in this session, branch and bound hopefully you will do it offline. So, let us look at this small example. It is a problem graph, as you can see. The nodes are labeled with letters. So, A, B, C, D, E, F, G, H and so on. The nodes have been drawn on a grid which is, let us say 10 kilometers by 10 kilometers or 10 miles for 10 miles if you live in a country where you measure distances in miles. So, the distance between two grid lines is 10 kilometers, and the reason why we do this is because we are going to be using a heuristic function to compute estimate distances, and because these points are on the grid and they have integer coordinates which are multiples of 10, it is easy to compute, at least in the example, the heuristic distance. Of course, if you are working with a real map which is used for route finding and you are implementing an algorithm, the algorithm will have no difficulty computing fractional coordinates, because that is one of the things machines are better than us, is to do this kind of arithmetic very quickly and accurately. Each edge in this graph has been labeled with a cost. This cost is the actual cost if you were to traverse that edge essentially. So, this is the cost that will add up to the final cost of the solution. The heuristic values are only estimates which are used for guiding search, whereas the edge costs are the actual costs which will be incurred by whatever is the application that is using this A star. And like we did in the case of branch and bound and Dijkstra's algorithm, we will see that we will keep adding the edge cost as for every node that we are going from the start node to the goal node. In our example here, we have chosen the start node I, which is in the middle of the graph somewhere as a start node, and this node W, which is at the corner as a goal node essentially. So, we want to see how our algorithms they find paths from start node to the goal node. Remember that we had looked at some heuristic functions already in this domain, which is let us say the route finding domain. One estimate of distance is the Euclidean distance, which is the straight line distance or the distance as the crow flies, and you can see that for one particular blue node and its 3 successors which are drawn in bold here, the heuristic distances are 7.21, 8.42 and 9.43, and best first search algorithm would presumably have this node to expand next. The alternative that we considered was Manhattan distance, which is also known as the city block distance, which assumes that we are living in some city which is got parallel roads both in the horizontal and the vertical direction, and the distance that you would have to cover is along those city blocks, as they call them. Now, remember that this is only an estimate, the Manhattan distance is only an estimate. The actual paths that our algorithms are going to be traversing are along the edges of the graph, but the heuristic distance is independent of that. It simply says how far are we, how far do we appear to be from the goal. The Euclidean distance and the Manhattan distance both give us estimates in some manner without looking at the graph, only looking at the coordinates of the two nodes. And you can see that even in the Manhattan distance case, this node, same node, whose now Manhattan distance is 10, appears to be closest to the goal node. In this graph that I have drawn, the distances are in units of 1, unlike in the example that we are looking at, where they are units of 10. Anyway, that does not matter, it is just a matter of scaling this thing. We will use a Manhattan distance for the sake of simplicity, and for the problem that we are trying to address, here are the Manhattan distances shown in blue with every node. So, for example, this value has a value of 80. So, you can see that there are 2 segments here and 6 segments here, and so, and since each segment is 10 units, okay. So, this one is not there. Yeah. So, these are the 6 segments. So, 6 plus 2 8, and so we have a distance of 80 essentially. Now, the graph does not depict the reality of the problem, and it is possible that there is a river running as shown here in this, and there are only 2 places where there is a bridge to cross the river. And so, clearly any solution which goes from the start node which is here to the goal node which is here would have to go through one of these two bridges, and we will see that all the algorithms that we are going to look at, in fact, the 2 algorithms to start with, which is best first and A star, both will find paths through these 2 bridges. But you will also observe that there are certain nodes, for example, this node with a value 70, this node with a value 60, and so on, they appear to be much closer to the goal node. So, obviously, both algorithms that we are looking at, because they are going to be using heuristic functions, they will head towards these nodes, because they appear to be closest to the goal. But from there, if there are no neighbors which are improving their prospects, they would have to in some sense retract and go back and try some other paths. So, in that sense, both best first and A star are complete algorithms, unlike hill climbing, which would have got stuck in one of these nodes, and both best first and A star will find solutions or paths to the goal. Best first is expected to perform faster, because it is only guided by the heuristic distance, and as we will see in the example today, that even though it terminates faster, it terminates with a solution which is worse than the solution found by A star. So, A star does more exploration, but it finds a better solution essentially. And later on in the next session when we meet, we will prove that under certain conditions A star will always find the optimal solution. The conditions will be, as you can expect, on the heuristic function. You can't choose any arbitrary heuristic function and get estimates which are useful in guiding search. The heuristic function must satisfy certain properties, and these are properties that I would urge you to think about, and also we will discuss them in the next session more formally. So, this is a graph that we are going to be working with, and I removed the labels nodes from the nodes, and instead we will use the f values, which is what the algorithm uses for picking a candidate from the set of candidates or the open list. But first we start with best first search, and best first search uses the h values, and the h values have already been labeled here. So, we will just show the open nodes in cyan and closed nodes in orange, and see how the algorithm proceeds. So, as any algorithm, you start from the start node here and then start exploring the graph, looking for a path towards the goal node. So, we put the start node in closed, and as I said, it is in orange or brown or whatever it looks on your screen. And once we generate, when we expand that, we generate its neighbors, and you can see there are 5 neighbors of the start node, and this arrow, red arrow, will tell us as to which is the best neighbor at any given point. So, these nodes in cyan will be the set of open nodes, and the arrow will tell us which is the best. So, you can see here that the nodes in open, one has a value of 100, another has a value of 120, this has a value of 120, this is a value of 110, this has a value of 90, and this has a value of 80. So, since 80 is the smallest, that is what best first is going to pick next, and this red arrow will tell us at each stage as to what is the candidate that best first is going to pick next. So, the next once it expands this node that it has just picked, its two neighbors, you can see the one and the one here, they will get added to the graph, and now they have gone into the open list. So, the open list is expanded, we have more open nodes, and the best looking open node is the one with the heuristic value 70. Now, if you were to looking at the hill climbing algorithm, so remember that hill climbing is a local search algorithm, it only looks at the local neighborhood of any given node, and if this is a node with a value 70 that you are going to expand, then it has only two neighbors, because there are two edges going out of this. One has a value of 80 and the other also has a value of 80. So, for hill climbing, this is a local maxima or local minima, and hill climbing would have got stuck at this point and terminated by saying that you can't find a path to the goal node. But as we have been saying, best first search is a complete algorithm, it is a global search algorithm, it does not throw away all these nodes in open that it has maintained. And so, when it expands this node, it generates new neighbors, in particular the neighbor which appears to be the best, which has a value of 80 this thing. So, keep in mind that the nodes in orange or brown are the ones which have been inspected, the nodes in cyan are the ones which are the set of candidates or the open list, and the best one is the one that is going to be expanded at each stage essentially. So, when it picks this node 80 and expands it, it will add its new neighbors, this one and this one, as well as this node it will find again, but since it is guided only by heuristic values, we will see that it will ignore this node completely, and as a result it misses out on the shorter path which is coming through that node to this particular node. So, when it expands this node, you see that this neighbor with a value 60 appears to be closest to the goal, and it does indeed appear to be closest to the goal, except for the fact that there is no edge going from there towards the goal, and that we observed was could be because, for example, there was a river running across that part of the thing. So, it does expand that node, but it does not find any new neighbors. So, it shifts its attention to this node with a value 80, and once it expands that, you can see that in some sense it is on the bridge. If you remember the river was running somewhere like this, and it is about to cross the bridge, and it will rapidly find a path to the goal node. And so, here it is, the goal node is on its open list, and it clearly the best node because it has a heuristic value of 0. So, it picks that node and finds a path for us. You can see that the path it finds does not look the best. We have already observed that this could have been better. This would have been 12 plus 12 instead of this 21 plus 12 plus 33, which is a long path to this fourth node. And the reason why that is that because it is guided by heuristic search, it is only looking forward from this direction, it is not looking backward to see if there is a could have been found a better path. It ignores the shortest path to that node. Also observe that the path that it did explore this node number 5, but the path to node number 6 is actually through path number 4, because 6 would have been generated as a child of 4 first essentially. So, in that sense it keeps track of who was the parent, and therefore, the path reconstruction algorithm will trace back the parents, and therefore, this is the path it has found. It has inspected 8 nodes numbered here from 1 to 3, 4 in the order in which it inspected them. 8th node was the goal node, and the cost of the solution it has found is 195, let us say kilometers. Let us see now what A star does with this same problem. Now, remember that best first search just ignored the edge cost, it was not concerned with the edge cost at all. it was only looking at heuristic distances to the goal, which are these values in blue that have been labeled next to that, and therefore, it simply rushed towards the goal, hoping to finish its job faster. Now, we come back to A star with this same problem, and what we will do is we will remove the node labels, and instead we will label the nodes with f values. Remember that f values are the sum of g values and the h values. The h values are the heuristic distances which have been labeled here for the entire graph, and g values will be completed as and when we computed as and when we explore more and more of the graph. We start off with the start node as before, and you can see that the label inside the node is 100, which is its f value. Remember, it is the f value, but f value is equal to h value for the start node, because g value is 0, because you are already at the start node, and this is the only node which is in contention. So, as all other algorithms, algorithm A star also begins by picking this node as the first node for expansion. For inspection, checking whether it is a goal, and if it is not the goal, then expanding it and generating its neighbors, and you can see here that it has gone into closed list. It has generated the same 5 neighbors that best first also generated, except that now the neighbors are listed labeled with their f values, and it will choose the node which is lowest in the f value. In this case, it happens to be the same node as picked by best first, but its value is not 8, which is what best first thought. Its value is 101, and this 101 is the sum of 21 plus 80. So, this 80 comes from the h value, and this 21 comes from the g value, and so it looks at the sum of g plus h values, and its value is 101. So, remember, this 101 is the estimated cost of finding a path from the start node to the goal node, which passes through this particular node, and likewise for all nodes on open, it is an estimated cost of a path from start to goal which passes through that node, and A star will always pick the one which appears to be the cheapest estimated complete solution. In this case, it is the value 101, as we can see here, and like best first, it generates its children, and the same 2 children are generated, but their f values are computed here. But you can see that this node with a f value of 102 was ignored by best first, because best first would have preferred this node with a value 70 as opposed to this value of 90, and after that it never found a chance to go back to 90, because its heuristic value was always less than 90. But A star has been able to recognize the fact that even though the cost of estimated distance of this node is 90 to the goal node, that is the estimated distance to the goal node. In fact, it is a Manhattan distance. So, you should draw it like this and not like this. And the estimated distance of this is 70. The actual cost of reaching this g value is 21 plus 12, which are these 2 h costs, is equal to 33. So, 33 plus 70 is equal to 103. So, the estimated cost of going through this node is 173, even though its heuristic value is less than the one that A star is preferring, whose heuristic distance is 90, but it knows that its g value is only 12, and therefore, the total estimated cost is 90 plus 12 is 112. So, in that sense, this is what I have been trying to emphasize, is that the A star algorithm looks both behind as to how long did it, how much did it cost to reach that node, plus how much will it cost to go from that node to the goal node, and therefore, its behavior is a little bit different from that of best first search. Best first search would have picked this node with an estimated cost of 70, because it does not look behind, whereas A star is looking at a combination of f and of g and h values and picks this node 102. So, once it picks this node, it adds its neighbors, and its neighbor has a estimated cost of 104, the new neighbor it has generated, and the node 103, which is what best first had inspected, comes back into contention and it becomes the best node. So, again it expands that. Now, notice that when it expanded this node 101, it found a new path to the node whose value was 122, but it did not prefer that path, because 122 was generated by adding up 22 and 100, and that is 122, whereas if we had chosen this path, then you would have had to add 21 and 21, which is 42 plus 100. So, it would have been 142. So, A star keeps track of only the best path and it ignores this new path. Likewise, for this node, it has found a new path, but it is going to ignore it, because clearly this other path that we spoke about earlier also is the shortest path. So, it keeps the parent pointer like Dijkstra's algorithm pointing to the best way of reaching that particular node essentially. So, now it is going to expand this node with a f value of 104 and h value of 80. As before, it generates that node which appears to be close to the goal node. As before, it picks that node and finds that it does not make any headway in that direction, and it shifts its attention back to a node which on the surface it looks to be in the wrong direction. The heuristic function says that its value is 100, estimated value is 100, and that is also reflected in the placement in this graph. Whereas, there are nodes with, for example, value 80, which seem to be better, but A star is picking that node with a value 100, with the h value of 100, and that again is because its f value is smaller, if f value is 122, whereas the f value of this is 126. So, A star prefers to explore that node, and in that sense it has this inherited behavior from Dijkstra's algorithm and branch and bound, that it will extend the cheapest estimated paths first. So, that is what it does here, and it has found another path to this node with value 143, which had found earlier, but this new path would have been 22 plus 23 is 45 plus 100 would have been 145. So, clearly it is not interested in that path of 145. So, it maintains this back pointer, which is the shortest path of reaching that node, but it shifts its attention back to this node with heuristic value of 80 and f value of 126, generate its neighbors, and as you can see here, it has shifted its attention back to another node whose value is 142 f value, because the other nodes are more expensive. So, it expands that, it finds yet another path to this node. The third path, the first path was the one that we found earlier, the second path was this, which was ignored, and the third path is also ignored. But at this point, this node has become the cheapest node, and it explores this next, and then it turns out that the example that I have constructed, it is heading towards a different direction from what best first did. So, remember that best first, once it reached here, then it found this 40 and then it headed directly to the goal and terminated there, because it was only looking at distance to the goal. A star is much more explorative than best first search, and even at that point where it looks like we have a node which is only 40 kilometers away, it is still considering a node which is actually 80 kilometers away, because it is also computing the actual cost found so far. And if you incorporate that, this value is 150 and this value is 144, and therefore, clearly this has more promise of finding the optimal path essentially. This this extra explorative behavior is necessary if you want to guarantee that you are not going to miss out an optimal path. And we will talk about optimality more formally in the next this thing. So, it continues here, and it so happens in this graph that it rapidly now finds a different path to the goal node, and you can see that it is at a node which is only 20 kilometers away from goal, or appears to be 20 kilometers away from goal based on the heuristic function, and adds the goal node to the open list, but it does not pick up goal node next. It picks up this node whose value is 147, which is less than the goal value of 148. Now, remember that the paths that we have found to the goal node, we know the exact cost, which is 148. The paths that we have found for this node to 147, it is only an estimate. It is an estimate because its heuristic value, its g value is 37 and its h value is 110, and the estimated cost is 147. But because this estimated cost appears to be better than the actual cost that we have found, it, like Dijkstra's algorithm, it will not pick the goal node till that has become the best. So, it picks this node with 147, and you can observe that at this point it has found a better path to this particular node. Its value has come down. It was 170 just before this node was expanded, and now it has become 150. It has found a better path, but 150 is not good enough to compete with the path that it has found to the goal, which is of 148. And observe that all other open nodes are more expensive than 148, and therefore, A star is kind of justified in picking up the goal node, and once it picks the goal node, because it is completely refined, it will terminate with a path of 148 essentially. So, this is the graph at the end of this whole process of generation that A star does. It has inspected 14 nodes, all shown in this orange brown kind of color, much more than what best first search did. Best first search explored only 8 nodes, but best first search found a path of cost 195, if you remember, and if you go back to the slides, whereas A star has found a cost of 148, which is of course much better than that. And I will urge you to compare this with branch and bound and Dijkstra's algorithm, which are known to find guaranteed, which are known to guarantee the optimal path. You will see that in this particular example, at least A star has also found the optimal path. Why it has found the optimal path is on the conditions that I had mentioned, we will put on the heuristic function, but we will see that I have chosen the heuristic function in such a way that A star does find the optimal path. We will discuss exactly what those conditions are under which A star is admissible, as we say, or it finds the optimal path, but we will do this formal proof in the next session. Meanwhile, this is a graph that it has explored. These dashed edges are edges that it also inspected, but ignored because they were not path of the optimal path. Like Dijkstra's algorithm, for every node it has a back pointer showing to what is the best way of reaching the node from which parent and so on, and the optimal path has been shown in this red thicker arrows, and you can see that it is a totally different path from the path found by best first search. This had to in some sense go to a node which appeared to be going in the opposite direction, because that is how it found a path which is a shorter length essentially. You can see that there were some nodes which this algorithm did not explore at all. These are the nodes which have no filled in color, and as an exercise, please try the Dijkstra's algorithm on the same problem and confirm that this cost of 148 that this algorithm has found is also the cost found by Dijkstra's algorithm. In fact, the same path will be found by Dijkstra's algorithm, but it would do more work than A star, because it would explore some of those nodes which we have not explored using A star. So, you can see that there is a gradation of behavior. The I stars does the most amount of work in terms of the number of nodes that it will explore, guarantees you the optimal path. A star does less work than Dijkstra's, it explores fewer nodes, 14 in this example, but under certain conditions which again I am repeating, we will study in the next session, it will also guarantee an optimal path. Best first search does the least amount of work, but it does not find the optimal path, and we can try and see that are there behaviors between best first and A star which will do less work, but hopefully give you optimal paths, or at least they would have a better chance of giving an optimal path, even if they may not guarantee the optimal path. We will look at variations of A star that do that as well essentially. So, if you were to list the path that has been found, you can see that the path is given here. It is the list of nodes starting with the node I, the node P, which is on the optimal path essentially. So, if you are asked to list the nodes, then this is the list that you would be expected to give in, for example, if you are writing an exam or doing something like that. So, I hope this has given you some good insight into how these different search algorithms, best first, hill climbing, Dijkstra's, A star, they behave on similar problems. We will look at some variations as we go along, particularly we will look at variations where you can save on some space, because we will, as we will discuss, A star also the space complexity depends upon how good your heuristic function is, and heuristic functions are not always very good, and therefore, maybe we have to adopt different methods to save on space, but we will come back to these later. What we will do next is to see as to under what conditions A star guarantees an optimal solution. We will give a proof of the fact that under those conditions A star will always find the optimal solution, and we will also show that if we have a more informed heuristic function which is closer to the actual cost of a path, then A star will do less work in terms of number of nodes that it will explore for finding the optimal solution. So, we will come back and do some of this formal stuff in the next session. So, see you then.